All right, let's get started. All right, our first homework is now due. Yeah, due right now. So make sure you submit. Right? I said like when you work in Canvas, you need to click submit, okay? And make sure that you're submitting to the correct one. So as I said, for homework one, we have two different links, okay? One for the undergraduate section and one for the graduate section, okay? And then homework 2 is posted. So this is our kind of like regular cycle, right? So when the previous homework is due, then we're going to post the next one, and you have 1 week to finish, okay? So homework 2, posted in Canvas, okay? It's due by next Thursday's class before the class time, okay? For homework 2, we have the one link for both sections, so you can just use that one. But then in that, you'll see the questions are slightly different, okay? All right, so any questions regarding the homework so far? Hopefully by now your Python code environment is working properly, because we do still have a little bit more coding in homework 2. Fine so far, okay. All right, and let's say by now, hopefully you have figured out like how you can post questions in Piazza, so you can get answers from our instructor team directly, or actually see our classmates helping each other. That's also very good, okay? Also, we have office hours, both like in person via Zoom, so just make sure you check the office hour information in the syllabus, okay? So you can come to our office hours with questions, okay? And then besides that, like, if the time doesn't work for you, you can contact us to see whether you can schedule a different time, okay? Because ultimately, we just want you to kind of plan ahead, right? Knowing that there's homework coming up, so you start early, and if you have questions, you have a way to get answers like before the deadline, okay? All right. So in the previous lecture, we finished chapter 2, okay? This is the chapter when we're starting talking about like what kind of data you have, what kind of like characteristics, right, you have in your data, and how you can measure similarity distance with your objects, okay? We then get into some of the pre-processing steps, right? So this is where you say what kind of data quality issues may exist in your data set, how you find those issues, how do you come up with ways to address them, okay? With good reasoning of what is the issue and then what particular methods you would like to use to address those issues, okay? So some of the specific things I'll talk about: cleaning, integration, transformation. Last lecture, we finished the dimensionality reduction. So all those are ways for you to kind of like prep your data, right? We then continued with the next chapter, okay? So this is where I say when you have usually like large amounts of data, okay, very diverse types of data, and you may be using it for different purposes, okay? So like for your course project, if you're just only getting like one or a few data sets, and you may have a bit of more of a kind of say more direct use of the data, then you don't need to go through all that. But many of those kind of like data warehousing management capabilities can be quite useful if you think about a larger scale or a more general support, right, for decision making, okay? We started introducing the idea of data warehousing, okay? So number one thing, right, we want to have a separate data store, okay? That's different from your productional database or data management system, okay? Because the general idea is that your production service is quite different from what we would do in the decision support scenarios, okay? So because of that, we want to build the systems just to be separate. They have different functionalities. We care about different performances. The usage scenarios are different, okay? So a lot of that is really, again, the reasoning, right, about what you're trying to do with your decision support, like type of processing, right? And then we talk about the difference between OLTP and OLAP, right? So one is the transactional processing, the other one is analytical processing, okay? So there are quite a few differences, and because of that, right? So we start by saying, okay, we want to have separate data source, okay? And then say, okay, separate, but separating what way? Like how different? Like what's the like key differences, right? So we start by saying, when you're trying to look for, like, say, for like data mining, many times you start with some subjects, so it's subject-oriented, right? So meaning that I focus on certain things where I'm trying to pull the data for my particular analysis, okay? What else? What are other ones? When you say data warehouse, what are some of the key characteristics? Does your data change? in the data warehouse? We say non-volatile, right? So the idea is that you don't overwrite your data. Okay, you can add new data, right? Because as you kind of grabbing information from more data sources, so then it's definitely good for you to add data, or you're doing some pre-processing or doing some kind of updates on the data you have. Always add to whatever you have. You don't overwrite, okay? Anything else? Subject-oriented, non-volatile. What's the time duration of your data? Longer, right? With operational like data stores, usually it's about the current status, okay? But with the decision making, we always try to look for historical data, right? You want to look at like a longer time, a much longer time duration, so that you can gain insights, right, from that larger amount of data. Okay. Also, another one is like integrated. So that's just related to the fact that you don't look at just one data set. You're trying to actually integrate data sources across different places. Okay. So besides data warehouse, we mentioned a few newer terms. Anybody can still remember? Data warehouse. We have data what? Data lake, okay? Data lake, the high-level idea is that, okay, like instead of like this enterprise view where you have full control of all the data you need, and now you're trying to work with all kinds of data, knowing that they just, well, yeah, you accept them as is, and then you're trying to work with the wider variety of data, okay? And later on, we're just combining these two. What's the new term? Lake house, okay? Data lake house, right? So the idea is, okay, I want to actually combine the flexibility and the scalability of data lakes, but then with this a bit of a more of the transaction support and a better structured data management, okay, of the data warehouse, okay? We also mentioned data fabric, data mesh, right? So those terms and general virtualization. So the idea is that there'll be data everywhere. They may be organized or managed by different entities. So a lot of times it's about how you integrate, right? How you connect those pieces so that you can get the data, you can get the data, like the services, right, on top of those kind of data to build up whatever you need for your problem. Okay, so those are just different notions, right? But a lot of times it's really the reasoning, right? From your side, it's okay, what kind of data do I need? What kind of data do I have? How do I use the data to bring out the value? Okay, from the different types of data, okay? And then we start talking about some of the more concrete things about how you organize your data, how you actually design the different schema of your data warehouse so that you can then run all kinds of operations or computation on top of it, okay? So star-shaped, if you kind of ring a bell, right? Star-shaped schema, so you have basically a star, right? Fact table in the middle, dimensions as the branches. You could also have the snowflake, basically just not one level, but multiple levels of connections, okay? And then this like constellation kind of thing. So you have multiple fact tables, and they are connected through their dimensions, okay? They may have some shared or overlapping dimensions. Okay, OLAP operation, we don't need to enumerate all that, but the high-level idea is that you basically want to say you can get drill down, roll up, right? So this is about how you get finer granularity, coarser granularity, because many times depending on what you're trying to do, you have some notion, right? But the data may or may not be at the granularity that you want. Okay, so you're trying to decide, okay, which dimensions do I care about, right? And for those dimensions, maybe you care about certain values. So you're doing this like a slice and dice as well, right? So you're basically picking out the information that is the most useful for your particular problem, okay? And then before we ended, in the previous lecture, we were talking about data cube computation, right? This is the general idea, right, in terms of, hey, if you look at data cube is this multi-dimensional data abstraction, right? So you manage your data as just multi-dimensional data, okay? But then as you're kind of operating, right, playing with your raw data, you can actually aggregate along different dimensions, and that is the term we're using as this kind of lattice of cuboids, okay? So you may have your base cuboid, that's the information with all the dimensions, but as you aggregate along certain dimensions, then you have those kind of topper level, right? So fewer dimensions and in an aggregated way, okay? So when you're looking at all this, right, so ideally you say, okay, yeah, give me my raw data set, I want to just build up everything, right? so that you have all the information available to you. So whenever somebody comes in, requests certain types of data with certain dimensions, certain values, you have a way to support it right away, okay? But then we ended here. Let me actually pull up this one. Sorry. So we were talking about like, okay, as you're doing the aggregation, you basically need to know how you do the aggregation or the computation, right? Because when you aggregate, okay, you basically pull in different dimensions, right, that is specified in the request, and then say, okay, I need to aggregate along certain dimensions, okay? So our like early example, right, you have so the base one is each individual cell may have the concrete value for each of the dimensions, and then at some point when we say aggregate along these locations, I don't like say I don't need the specific location information, aggregate all of that, or you can aggregate along the customer group. So basically you're doing the aggregation like using the cuboid cells, and you're building up the overall lattice, okay? So this gets to the very last point, right? I was asking you to think about the scenarios, okay? So the idea is that, okay, I have the potentially, right, the whole lattice of all the cuboids I could do, right? That potentially may be used by an upper level request, okay? So there are a few ways in terms of how much you pre-compute versus how much you do on demand, okay? So full materializations at the basis is I want to pre-compute everything, okay? That's doable, right? Because you already have the base cuboid information, so you basically just take all the possible combinations and calculate like all the values, the cuboid cell values and all the different cuboids, okay? I can do that, right? Another one on the other end is like no materialization. So that means I don't pre-compute anything, okay? I just take whatever raw data I have, store it there, but I don't do other thing, okay? And then at the runtime, right, somebody comes in, okay, says that, okay, I need those cuboid cells. So that's maybe an upper level one. So then you do the computation. That's more like on demand, right, or online computation, right? Somewhere in between is partial. So that means I don't pre-compute everything, but I compute something, so that I hopefully can leverage, right, whatever I have pre-computed, and then like adding whatever online computation I may need. Okay, so understand the difference of those three scenarios? Clear? Okay, now let's look at the performance, pros and cons, okay? So what is the benefit with the full materialization? Why do we want to even consider that? Anybody? Come on. Yes. Yeah, everything is pre-computed, right? So at the runtime, if you need anything, all you need to just pull it out, right? You don't need to do the computation on demand. So that basically saves your latency, right? Definitely reduce your latency because only need to pull the information instead of computing it. But what's the downside? Maybe it's not as complete, but I'm doing full computation. I'm doing everything. So I'm pre-computing all the possible information that's needed.
It takes a lot more storage. You store a lot more data points.
Yes, yeah. So because of full computation, think about all the possible combination, it's huge, right? So if you need to compute all that, one, it takes a long time, but that's offline. So you're probably still fine, okay? But then you would need to store the information so that you can get the data quickly, okay? So storage space is a big thing, especially when you have reasonably large data sets and a lot of possible combinations, right? And sometimes this is also even considered wasteful because a lot of those computational pre-computed things may not be even needed, right? So you're spending all the effort, you're spending the space, but turns out, well, it's not being used. Well, sometimes, of course, it's always good to have some sense back. So if you value a lot more about the latency, right? Say I really need, when I need something, I need to get it right away, versus, oh, well, maybe I can take some time to get the answer to you. So this, again, depends on your application scenarios, okay? But you already see it, right? The pros and cons of full materialization is that you spend more effort upfront, you need a larger storage space, but then it can be much faster at runtime, okay? If I don't do anything ahead of time, so of course I'm not wasting anything because I haven't done anything yet, right? But then what's the downside? Execution time, you need to do it online, right? So now you get a request, you don't have it pre-computed yet. So you need to do it like on the fly, okay? So that can be quite slow, okay? So you can see, right, on the two ends of the spectrum, it's either too much or too little. So we say, okay, let's do it in a partial way, right? Partial is good, right? Somehow you decide. Like some of the computation you want to do ahead of time, right? So apparently here, okay, do I randomly pick whatever I want to do, or I have some way, right? So generally, you want to use some kind of heuristics, okay? What would be some heuristics you think may be useful? If I'm saying I'm trying to decide doing some pre-computation. Raise the hand, no? Okay, yeah, if you, so the point is that if you can download the data you need and kind of ignore, or in a way, not use the other one that you don't need. So that assumes you have some prior knowledge, right? That let's say, okay, I know that these data are more likely to be used versus the other ones that are maybe less likely. So example, like say, I know like say, like this branch, right? Is this branch is important for us. I see like a lot of analysis or things that are needed. So I probably like say prioritize computation for that particular branch. Or I know like for this categories of products, right? They're like, they carry more weight. Let's say they actually generate more revenue or somehow, right? So usually you're leveraging some kind of a prior knowledge or domain kind of knowledge, so that would help you to guide that, okay? But if I don't know anything, I can just observe, right, how things are being used, right? Because after you observe the data requests come in, what kind of computations you're doing, on what dimensions, at what level, those are the things you can learn over time, okay? So just there are a few ways, right, for you to collect this kind of information that can then be used as heuristics to guide, right, your partial computation. Make sense? Okay, so as you can see, right, usually, always there's no, like say, one answer that is much better or always better, right? But it's about the reasoning. When we say that, okay, there are different ways of doing things, okay? First, understand how they're different, right? And then ask about the question about, okay, what kind of performance metrics do I care about? How important, right, is one versus the other? And then you do your reasoning and then say, okay, let's do this, right? Sometimes say like the full materialization is fine because, well, say, it is time critical, and also actually we actually have a way to support that, so the cost is actually reasonable compared to the benefit I get, right? But you just need to do that reasoning. Okay? Clear? All right. So here we're just saying, okay, we want to compute, right, the data cube. But here the notion is still that, okay, somehow we expect, right, the whole latitudes, the whole cube itself may be potential use. But in the real world, we realize that a lot of times, right, we don't care about like those smaller items or things that are not important enough, okay? So many of you probably have seen those iceberg, right? When we say tip of the iceberg, what does it mean, right? You see a little bit, right? This is the iceberg, but you can actually see the whole thing is much bigger, okay? All right. Of course, in the actual world, you do care about what's actually beneath, right, the surface. But in the data mining scenarios, a lot of times we care about things that are significant enough. Okay. So meaning that if you identify certain patterns, if you're changing something, you need to kind of move the needle some way, right? If it's insignificant, right, then you can ignore. In a way, if you're prioritizing things, right, you will focus on things that will have bigger impact. Okay, so this is the general notion. Okay, so we're using the term like iceberg cube, meaning that even though the overall like cube space is huge, okay, but we only need to focus on the ones that are significant. Okay, so typically we're using this term like a support or minimal support. Okay, you can use that as some kind of frequency or significance count. Okay, so usually you can say choose some kind of minimal support and say I only care about things that are sufficiently important. So if you talk about your sales amount or revenue, then you can set some threshold. right? Depending on the size of your business, and say, okay, I only care about scenarios when they like combined revenue is above $1 million, okay, or billion, depending how big it is, right? So you have a way of specifying what is more important, okay? You can, of course, if you want, you can like adjust that to support, right? Start with maybe a higher value, so you're looking at the top ones, and then you can lower it so that you start looking at some of the one that's like in the middle, but still can be useful, okay? So with all that, right, then the general idea is that, okay, we want to use that information, right, so that we only need to focus on our computation of the cube or data cube of the ones that are more significant, okay? So that's a high-level notion, but how do you do it, right? Of course, like in your actual computation, whenever you see that data value, like if you pre-compute everything, and then you can do the pooling, right? So in this case, you still spend all the time doing the computation, but it already saves you in the sense that, okay, I don't need to store everything, right? Since the computation time still the same as a full materialization, but I probably need to store like only a small fraction of the overall data. So your space saving is much bigger. But that's one scenario, okay? But sometimes we say, can we actually not do everything, right? We don't want to pre-compute or do all the computation and then filter out, okay? So there are a few notions that you can leverage, okay? So consider example, right? This is like one way, say, how you actually specify, right, your iceberg cube computation, okay? So here we start by saying, okay, I want to compute a cube. This is using my, like, say, sales iceberg. So that means I'm using my sales data, right? I'm computing iceberg cube, meaning that I'm using some kind of threshold to cut it. Okay, the information, dimensions I have, right? Month, city, customer group, and then count. Sales info, that's my raw data or base cube, okay? And now when I'm trying to, so cube by, so this is what I'm trying to do, right? So I'm kind of aggregating, right? So I need a month, city, customer group, but now I'm using this count function, right? Basically count, right? How many instances you have for any of those cuboid cells when you aggregate them, and then when they're above your minimal support value, that is the information you're going to keep, right, in your iceberg cube. All right, so to do that, there are actually quite a few techniques, okay? Some of those are quite intuitive, some of those are probably customized, giving your data sets, giving your problem setting, okay? But here are some high-level ideas, okay? So keep this example in mind, okay? So I have, like, say, sales by branch, day, item. So basically say, okay, for any sales information, right, record, you have something saying that, okay, which branch, which day, and then, like, which item has been sold, right? That's the base information you have, okay? So as you're trying to figure out, right, pooling or like, like removing ones that are not significant, right? So always, because we're trying to remove things or like compare, right, if they're below or above my threshold, right? So sorting, hashing, grouping, those actually generally make sense, right? Because like if you have a way of sorting, so they can start with the bigger cells, right? The items that are more significant, right? Or if you have some kind of grouping, right? So in our example, right? So if you can do grouping, say by branch or day or item. So here is one important notion, okay? This is related to the unique values you may have, okay? Think about a branch, right? Of course, like depending how big your business is, you may have certain number of branch offices, okay? And then you have day, how many days you're talking about. You may have a daily information, right? And then you have number of items, okay? So assuming in a reasonable setup, right, I may have a dozen branches, okay? And then have maybe over, say, 5 years of data. Okay, so 5 times 300 something, right? So that's like 15 or let's say closer to 2,000, okay? Items, my store has maybe millions of items, okay? So if I have all that, okay? Now if I want to do some grouping or sorting, like which dimension I would like to start with? Do you want to sort by item or sort by branch or sort by day? This is related to the unique values. Sorting by branch, that means I have maybe a dozen unique values, right? I can probably quickly get to, right, the sufficient support, and maybe I can remove those, like the branches that are kind of below my support value. So I don't need to worry about anything coming from a particular branch. That's one way, right? But then if you sort by item, okay, then you say, okay, I have millions of items, so I need to sort, right? Because there are possible millions of unique values, okay? So you sort by items, that takes a long time, okay? And when you aggregate, right, you may not have sufficient like values yet, but then in this case, you cannot remove them yet because you haven't finished everything. You see what I mean? Because it's a huge data set, right? So if it's a branching, when I finish one branch, I know I'm done with that branch, and I can already decide whether this is above or below my threshold, okay? Items take much longer to sort, okay? And the grouping also takes much longer, and it takes longer before you can decide whether you can print it out or not. Okay, that's just one example. But let's look at another one, okay? The aggregation, okay? So the idea says that aggregation from the smallest child when multiple child cuboids exist. Okay, what does it mean? Okay, supposedly, right, I want to, like, say, compute the branch only cuboid. So that means I only care about a branch. I don't care about the day or item. So that means I can take either branch and the day as the lower level cuboid, right? Or I can aggregate from branch and item. Okay? So if you're trying to visualize this, okay? So branch and the day as a combination, okay? Versus a branch and the item as a combination. Which one has more possible values? Branch and the day or branch and item? Somebody, sorry? Branch and the day has more values, more unique values. Days, like we count, if it's 5 years, it's like closer to 2,000, right, days. But items, I have millions of items. So which one? So branch and day, right, will have smaller number of unique values or smaller cuboids. Make sense? Okay, compared to branch and item. Because if you're keeping unique branch values and unique item values, it's a huge combination because you have millions of items. Make sense? Right? So in a way, because ultimately you just all aggregate together, right? But if I'm taking branch and the day, now I'm just only aggregating along the day dimension, right? And that is about 2,000 entries, unique entries. But if I'm aggregating from branch and items to get to my branch, so now I need to aggregate along item, and there are millions of items, right? So that means you're working with a much bigger cuboid if you're using the branch and the item cuboid. Make sense? Hope you're getting the difference here. Because the idea is that because the end value will be the same, right? But either you're like aggregating by a dimension that has fewer items already, so you're adding up basically 2,000 values, okay? Versus you're aggregating along millions of values. But they give you the same answer, same result, right? Okay. So those are just high level, right? Optimization techniques. So the general idea is that how you can like prioritize your computation, work with smaller kind of like cells, right? So that you can quickly pull out the information you need and then decide whether you're above or below the threshold, right? Okay, so let's look at a few more concrete methods, okay? So actually like in the literature there are a lot more methods. The textbook covers a few, and we're going to like briefly talk about it, okay? But in this case, like we're not trying to say like get to all the technical details so that you can implement and run it. But I want you to understand the high-level idea in terms of why it works and why it's more efficient than the kind of like brute force computation approach, okay? All right. So the first one is called multi-way array aggregation. Starting point, it is trying to do a full computation, okay? So it's basically trying to compute all the possible passes or aggregations, right? So that you have all the cuboids you need. For example, if I have, say, ABC, those are the 3 dimensions I have as a bait cuboid. And then I need to compute AB, AC, BC, right? And then, of course, I have a way of deciding whether I want to get A from AB or AC, but somehow, let's say I choose, let's say it's coming from AC, B is also coming from BC, C is coming from BC. So as you can see, right, I'm not computing all the possible branches, but I will compute all the possible cuboids and all the way to the top. So when I finish, I have everything computed, right? All the cuboids, all the cuboid cells are computed. So it's a full computation. Okay, but in this case, okay, I'm still computing everything, but I can do it in a more efficient way, okay? So this actually has to do with the fact that when you have a huge data set, your data, the whole data set, right, cannot be fit into your main memory. Okay, so this is the basic, right, computer systems, right, memory access versus like hard drive, or even if you need to go to another machine to get to the data. So anyway, say memory access compared to, like say, hard drive access. Which one is more efficient? Memory, okay? So if the data is in memory, the access is more efficient, and you can do a bit more ad hoc, right, direct access of the individual values, okay? But if it's on the hard drive, it takes longer, right, to go to the hard drive. Also, now random access will be much smaller, slower, because you have to move to, right, you have to move the head of the hard drive, like to the reader, right, to the particular position, and then read out the information. Okay? So, one, of course, when you can fit your data into the main memory, great, that's more efficient, try to do it, right? But knowing that when you have to go to the hard drive, scanning data is much more efficient than randomly accessing data at a time, okay? We got this, right? So this is the main difference, and that's actually is driving a lot of the design decisions, okay? So what we're trying to say is that, okay, in this case, yeah, my data set is too big. It's not all in the main memory, okay? So I have to go to the hard drive to read out the data, okay? So if you think about, right, the brute force calculation would be that when you're computing ABC, well, actually you have ABC, right? When you're computing AB, you can read out, scan through, right, scan through the ABC data set, you can compute AB. When you need to do, question? Okay, so the questions are like, is it always better to have data in the memory versus going to the hard drive? Usually, yes, because it is just faster. But why we still need to store data in the hard drive? Because the main memory space, well, it's much bigger nowadays, but still limited. Okay? So I think nowadays, I don't know how many, how big your memory space is, right? Nowadays, if you have 64 gigabytes, 128, those are usually already the pretty good machines, right? But if you talk about your data sets, right? Data sets, usually I'll say, well, in our project, we don't get that far. But nowadays, with most of the real-world projects, for example, we're working with terabytes of data, okay? And I know like some of my colleagues, they're working with petabytes of data, right? So most of the times, okay, a lot of times you'll find that your data set's too big to fit into the main memory, okay? So that's why now we're talking about how we can work through this, right, in a more efficient way. So as we were just saying earlier, right, when I scan ABC once, I can compute AB. When I do AC, in the brute force approach, I go to the disk again, do another scan, I get AC. You can do it, but it's a little bit wasteful, right? Because the information you need, ABC, is already there for you to compute AB, AC, BC, and actually AB, B, and C, and all the way together, right? So ideally, you only need one scan to compute all this. Make sense? Right? So instead of breaking the task like, oh, now I want to compute AB, and then AC, and then BC, and then I can compute A, you actually say, I can do this partial aggregation as I'm reading through ABC. But when I'm done with the whole scan, one time, full scan, I will have all of them computed. Okay? So this is one way to illustrate it. Okay? So as we said, right, these are my ABC. That's just a three-dimensional, right, cube. Okay, So each of those, let's say if we're doing this like 1, 2, 3, 4, that's my scan order, right? I'm scanning through the cuboidal cells one by one, okay? So when I do 1, 2, 3, 4, so each value would already be integrated into whatever the partial thing I'm trying to compute, okay? So if you look at this projection here, so this one, this is A, this is B, this is C. Okay, so if you project this way, so meaning that this 2D thing, you are aggregating along which dimension? C, right? When you go this way, right? All the C values are aggregated, okay? But if you go that way, so like this one, okay, then you are keeping B and C, but now dimension A is aggregated. See what I mean? Hope you can read this. Like it's a little bit complex, okay? But the high-level idea is saying that when I read, say, 1, so this value goes to here. It's a partial. It's not done yet, okay? But I know it will be mapped here. And then 2, similarly here, and 3 and 4. Okay, so when I'm done with 1, 2, 3, 4, I will have the partial value already kind of entered, right, for this one. But that's interesting here is that now after this one, because I'm projecting along the A dimension, I already have 1, 2, 3, 4. That's all the values I need to compute this cuboidal cells, right? Similarly, like if you do C, so you can see again, I only have partial value. But the high-level idea is that I read that value once, and I know where that value should be incorporated for my complete computation. Make sense? Right? So as a result, right, so I can save in terms of the data scan time, right? Instead of multiple scans for each cuboid, right, I have a way of scanning once and actually already have the data calculated. So when I'm done with the full scan, I have everything. Okay? All right, one more. Computing in reverse order. Okay, what does it mean, right? Earlier, we were saying that we start with ABC, right? And then I like compute A, B, and B, C, and then I get to A, so individual. So I go from the base cuboid up, right? But then remember what we're talking about, this is minimal support, right? So with the minimal support, what is interesting? If you know that, if you start with from the top, because you care about like enough sales or enough revenue, right? It has to be a lot above that threshold. So once you get to a point that is below that threshold, what about that? All the branches below it. Because if you think about, right, so if you think about those hierarchical branches, right, so for example, A is a branch, okay, a branch location. Okay, so this is a, hello, Boulder is probably, well, Boulder may be small. Okay, let's say Boulder has a branch, right? Okay, if the aggregated, let's say, revenue for the Boulder branch is already below my threshold. So anything, if I refine it further, for example, like, okay, I know the total revenue, to say, is 500K. It's below my, say, 1 million threshold, let's say. And now, does it even make sense for me to break it further in terms of, by, like, say, categories, like what type of item it is, or by whether it was sold in this month or the previous month? Does it matter? I don't care. It's always below my threshold. You see the point? Because the aggregated value is below my threshold, and if you're separate, like splitting it further, that value will only be smaller. Make sense? Yes or no? Is this part clear? So when you kind of keep splitting things, right, refining things. Okay, so if you visualize here, so all is like, okay, for example, like for my company, I know the total revenue. That's the value I already have. And I have the, like say, I have maybe the base information, and actually I have the individual records, right? But what I'm trying to do is that I'm trying to keep going down, like refine it, to figure out, okay, which branch or which like year or which month or which category of items are more significant, meaning that they're above my threshold. So I want to pay attention to those places, right? So as you keep it down, for example, like here, like A says the branch, and then you have, say, time, and then you have like customer group, and then you have the categories of the items. So you're splitting by different ways, right? As you split, you may realize that, okay, for example, like in this case, right? So this one is already below my threshold. So that means, say, I'm splitting by a certain category. I don't know which category. Item aggregate may not be as high. Let me see. water bottles. Let's see. So you somehow get to say like category of say like the items like household items, but they don't add up to a value that is significant enough, right? So once I get to this point, I can already decide, okay, I don't need to do any further computation below that branch because it's not going to be above my threshold anyway. Okay? So that's a high level idea. So what I want to do is like I want to keep divide the dimensions, right, into partitions so that I can facilitate iceberg pooling. Meaning that keep dividing when it's small enough below my threshold, I stop, right? I only focus on the ones that are still significant enough or above my threshold. Okay, so if you're interested, you can read the paper. It's a lot more details. We don't want you to, like, you don't need to understand all the details. But I want you to at least, like, say, know the notion of this is top-down approach, right? Top-down, you keep splitting until you're below the threshold, and you stop there. Okay? That's one thing, partitioning, right? So that's one key idea about partitioning. But then also, you want to do some ordering. As I said, right, if I have some way of ordering things, and I can quickly spread things out, for example, items, right? By items, if I can, because you have millions of items, right? Even though your total may still be a big number, but once you split, right, by a huge number of like many branches, then you'll probably get smaller values, right? So many of those like branches will be pruned out right away, and you only need the remaining, like smaller, like maybe a few bigger branches. Okay, that's the idea. Okay, one, you want to partition. Keep partition until you are below the threshold. You can stop earlier, right? Second, you want to order so that you focus on the ones that are more significant and quickly prune out the ones that are insignificant. Okay, those are the high-level idea. One more, high-dimensional data. Okay, so usually what do you mean, like how many dimensions are you dealing with? Think about the data sets you had like for your homework one. How many dimensions do you have? Pick a number, just if you remember. Anybody remember, like for your homework one, question one, answer? How many dimensions you have for your data set? Somebody? Come on. Sorry? 29, okay, that's one number. Anybody go above 100? No? 100? 152, okay, all right. Anybody have seen maybe 1,000? Not yet? Okay. All right. So in the real world, okay, a lot of data sets are high dimensional. What do you mean by high dimensional? Okay. There are different ways of defining it. But earlier, like, as people realize that like, when you're above 15 dimensions, it's already pretty hard to separate the space and have a like efficient way of managing things. Okay. Just as a rule of thumb, anything that's above a dozen is already getting hard. So if you are way above that number, right? Close to 100, above 100, or even getting to 1,000. And of course, if you talk about like document, right, the words, right, word vectors, right, then you're talking about not just thousands, right, huge numbers. Okay. So the first thing you know is the term curse of dimensionality. The general idea is that like, whenever you add a dimension, right, and that dimension of course has the possible values, right. So you basically like all the possible combination of your vector, right, or your like object description is going to grow exponentially. Okay, so think about like if you take like my students here, right? If you ask, I just ask a gender, it's only 2 values. I only need one line to split, right? Okay, but then if you add in age information, you add in degree program, I add in each of those individual courses you may have taken, right? Then the possible combination becomes big and huge quickly. Okay, so that's the notion, right, of like curse of dimensionality. Okay, that's not good, right? Because when you're trying to look at your data sets, you're trying to like somehow compare and separate. So you want to figure out things that are similar versus things that are different. So if the space is too big, it's hard. Okay, luckily, right, in many real-world settings, even though your data may be high-dimensional, but you usually like start with some more like, usually you're looking at more like subsets, okay, or subspace, okay? So if you like some of the real world observations that when you do like OLAP, like when you look at the OLAP requests, many of them only focus on small subset of dimensions. Great, right? Now the questions are which ones, right? If you know it, right, you can focus on those ones. This also connects to our earlier heuristic. If you want to do partial materialization, if you know certain dimensions are more typically used, then you can start with that, right? But here, what we're trying to do, right? Again, we're trying to do the pre-computation and the online computation, right? So my partial calculation, right, materialization, basically works like this, right? Instead of computing everything with all the dimensions, I pick out, right, subsets of dimensions. Those are called as shell fragments, okay? When I have those smaller, right, subsets, and then I can compute, right, whatever a possible combination. But since it's much smaller, I don't need a lot of computation. But I have a few of those, right, for those shell fragments. And then at runtime, I can just dynamically, right, combine and compute on top of it because I already have some of those kind of bases, right? Okay, so let's look at one example. So here we have a transaction table. Okay, so this is one way to read it. Right? You have say transaction ID 1, 2, 3, 4, 5, and each one say in that transaction which items are being purchased, right? Okay, so you say A sub 1, B sub 1, C, whatever. So that's how you read it. Okay, when you have this, right, already you can check. You can build this what we call an inverted index, okay, or value index list. So the idea is that I want to figure out, okay, this particular item, like this attribute value, right, has occurred in which transactions. So for example, like A1, I can see A1, A1, A1 here, and then nothing else. So A1 occurred in transaction 1, 2, and 3. Simple, right? And also you have a way of counting. So that's, they'll say, okay, 3 times. So A1 has occurred 3 times together, because I always care about the frequency or the support values, right? Once you build up this, you can then compute the shell fragments and also use the higher level computation. Okay, so supposedly, right, I have A, B, C, D, E, F, all those are my possible dimensions, okay? Instead of computing all the possible computations, combinations up front, I want to say, okay, I want to break them into kind of subspaces, right? Okay, so I say ABC, that's one shell fragment, DEF, that's another one. So I'm building a cube. This is a full cube for ABC, okay? And also I have the full cube for DEF, okay? Once you get that, remember since we have those lists, right, you can do this kind of intersection, okay? So this is actually very similar to the search engine mechanism, if you remember. How do search engines work at the very basics, right? You have keywords, right? So when user type in a keyword, and if I have this inverted index saying that this keyword occurred in those documents, right? You can pull out the corresponding documents. And if I enter multiple keywords, say, okay, I'm looking for something that has all those keywords. Then you can take the individual list, right? Say this keyword occurred in those documents. This keyword occurred in those documents. You take an intersection, right? This is just a set intersection. When you do that, you get a list that says these are the documents that contain all those keywords in the query, right? So similarly, that's what we're doing here, okay? So we have those subspace saying that, okay, ABC, any of those combinations occurred in those transactions, and then DEF, for example, here, the DE cuboid will say, okay, the possible combinations and then which transactions, right, contain those combinations, all right? Once you have that, right, all you need is take this combination, take the intersection, then you can build up what is called instantiated base table. This is a table containing all the transactions that have those items that the users are looking for. That's the intersection of those lists that we have. Once you have that, then you can do your online computation to figure out, right, the cuboid cells, and then if you do any pooling, then you can do it on top of it, okay? So as you can see, right, instead of starting with all the possible combinations, which is huge, right, and usually not feasible, I started with the smaller subsets, and I have some pre-computed, right, smaller cuboids or cubes, okay? With that information, especially those inverse index, I can quickly pull out the ones that actually contain all the information that I care about. So those items, those attribute values, right? Now I work with a much smaller table. We call it the base table. It's much smaller. And then using that, you can just compute whatever you need. Okay? Yes?
So it's faster to figure out what's in the smaller cube and combine it all afterwards?
Yeah, so the question is it faster to figure out what's in the smaller cube and combine it afterwards? Yes, that is what we're doing. Because here, I don't know what will be used later, right? For the smaller cubes, I'm actually computing the whole thing, all the possible things, okay? But because I have those all pre-computed, and I have this, you can view this as some kind of like index, right? It's a reverted index, okay, or inverted list, okay? With that, you can quickly do the intersection across those like cuboid like cell values, okay? So you can quickly pull out only the ones that are satisfying the particular constraints you put in terms of the which dimensions and which values. Does it make sense? And that computation is more efficient compared to like the overall, because you have all the possible dimensions, and then you can, as I said, if you want to pre-compute everything upfront or doing everything like on demand, that will be either too slow, right, or too much computation upfront. Okay? All right. That kind of ends our discussion of chapter 3, okay? So here we're talking about the data warehousing, online analytical processing, so some of the high-level thing. So here, I want you just to have this kind of contextual, like conceptual understanding of many things, right? So like why we need a data warehouse, what are the key characteristics of a data warehouse, okay? And also from data warehouse to data lakes, lake house, and also some of the data fabric, like what's the difference, right? How they are trying to like leverage different types of data and different services, okay? And then we kind of get a little bit more of the like the difference between OLTP, OLAP, right? And also like how you can support, right, different types of computations, okay? So really for this, as you're reviewing the slides, I want you to just understand the high level and like the reasoning of those concepts and why we're saying one is better in what way, okay? So if you go to the textbook, if you start reading the textbook, how many have actually read chapter 3? Everything? It's a lot, right? You probably noticed this, right? The textbook has a lot of information, okay? So I also get this question about like how much is expected for the course, right? So textbook has a lot of information. I definitely encourage you to read the textbook, but don't worry about like getting all the technical details. It has a lot of information, okay? So as you're reviewing the material using the slides, okay? So the slides I'm mentioning, those are the ones I want you to at least understand. And many of them you'll see, right? When I have concrete examples or the computations, right? That is when I want you to actually understand how that computation is done, okay? But many of the other ones on the slides read about the conceptual understanding. Make sense? So they're just different levels of things, okay? Our expectation is not for you to, like I say, memorize or understand everything in the textbook. But the homework assignments, make sure you get all that, okay? So those are the, like say, concrete, like calculations or things that we like to, I want you to understand. The lecture slides, those are the ones I want you to have a conceptual understanding. And then later on, when we get to some of the core techniques, this is actually my next slide, okay? Once we finish this, we're going to have the second part, which actually covers quite a few key chapters, okay? Those are the core techniques, okay? We will be going through different methods for doing different, like analyzing different types of patterns, and there will be examples showing you how to do various kinds of computation, and they will occur in the homework assignments. They will be occurring in the midterm exam. Okay, so those are the things I want you to have concrete understanding and also concrete understanding how to do the computation. Okay, but a lot of the other things in the slides that we cover in the class, and those are the things I want you to have like the reasoning, the reasoning behind it. Why this is this way, why they, like this one's better than the other one in this way, okay? So we'll, of course, do another review before do the midterm exam, so you'll find there, but feel free to, come to our office hours so we can talk about more, but just knowing that the textbook has a lot more information, okay? It is very useful, right? If you want to actually like learn more about that, those actually provide very, very good information, but don't worry about like getting everything like covered or figured out for the course. Okay, so So we're actually now finishing the first part, okay? Basically the intro, okay? Understand your data, pre-processing, data warehousing. So this is all the kind of prep stage, okay? Part 2 is when we cover the core techniques. That actually has quite a few chapters. And then part 3 is only very end of the semester. That's what we're going to talk about, like some of the more complex scenarios and some of the, like really the frontier of data mining research, okay? With that, I have a little bit of time, so I'm going to switch gear a little bit to talk about course project. Which week are we in? 3, okay? Thursday, week 3. When are we going to do the course project proposal? Week 5, okay? So we're kind of a little shy of like 2 weeks away, okay? How many of you have a team already? Okay, a few, okay? How many of you are, say, kind of, either say you have a tentative team or you are already actively looking for a team? Hopefully more. How many of you haven't started yet? Okay, all right, okay. So that's just like a timeline check, okay? We are 2 weeks away from the proposal, okay? As we have said, right, we do have this pretty extensive component in the course, which is 40% of your final grade. That's for the course project, okay? Of course, we don't do it in 1 week or 2 weeks, okay? We actually have almost a whole semester to do it, okay? But for the proposal, it is happening soon, okay? So just a little bit like reiterating, right? I really want you just to do a hands-on project. That's one. Second, I want you to come up with your own project ideas, okay? It's not easy, it's challenging, okay? But I think this is actually a very, very important skill and a very important practice, right, in terms of data mining. Because a lot of times, you need to ask the right question. If you ask the right question, or you have the right data, you have the right way to do it, you will come up with something that's valuable, okay? If you're just being told to, okay, go do this calculation, plot this thing, and report back to me, that is useful, but it's not as useful. Or the value is smaller, let me put it that way, okay? So I really want you to kind of like just get into this kind of like practice and also just like comfortable saying that, okay, I don't know what I'm going to do, but let me explore what's possible, okay? That's really the idea. All right, starting point. How do you choose your project? Okay. Remember our like the 4 views of the like data mining, right? What kind of data you have, what kind of knowledge you're trying to learn, right? What kind of applications it may be, and also techniques, right? Of course, like we're only in week 3, and by the time you do your proposal, we'll be in week 5, so we haven't really covered a lot of techniques yet, okay? So at that point, I don't expect you to have spelled out, right? This is what I'm going to do. I'm going to apply this method on my data to answer this particular question. No, this is really your problem formulation stage, okay? Starting point. What are you interested in? This is the part that I really like want to like the drive, because drive your project. You want to be working on something that interests you. You are curious about those questions. You're curious about the answers, right? And then there's more value, and it's more enjoyable throughout the process, okay? So really start by saying, okay, what are you interested in? Right? You may have very wide, it doesn't have to be all big academic, right? I have had students, right, so really look at a wide range of things. Things they are interested in, or things they always wonder about, right? Or talk to your friends, or your family members. If they may have something they're always like wondering about, say, oh, I can help you, right? So those are all things that's actually a very good starting point, okay? Who on your team? This is gets to the point, is like I want you to work on in groups, because data mining, really, like, I really enjoy it, like when you're talking to people. If you just say, okay, sit in your desk, like wrangling through a huge data set, yes, it's still valuable and useful, but it's a lot more fun and actually more productive in many ways that you have a team, meaning that we all come with different backgrounds, we have different perspectives, we have different skills, but when we talk about, right, the kind of the problem at hand, you always find some interesting ideas coming from each other, right? So that's really like the like one key motivation to work in groups. So some of you already asked, oh, can I work by myself? I'll say, I'm generally open to that, but I always encourage, like, try to find a team first, okay? If that doesn't work out, then talk to me, and I'll see, like, whether your scoping is appropriate for your individual project. Okay, but when you talk about your team members, right, always think about it, what your interests are, what kind of background you have. As I see in Piazza, like the forums, like people are already talking about, like, what they have done, what kind of things are interesting. That's actually how you can connect, right? I already mentioned that we can form teams across sections, undergraduates, students or graduate students, online section, or the in-person, whatever, right? As long as the team can have a way to work effective together, great, okay? Relate to that, data, okay? How many teams have already checked out the data? You know you will have what you need for your project? Any teams? I know we have a few teams. Or at least like, if you're exploring your ideas. Do you know the data set you need is available? Nobody? Okay, start checking, okay? It's important, right? So that you can really not do your project if you don't have data sets, okay? So as you're kind of exploring what things you're interested in, what kind of problem you like to explore, check, right? What data sets are available, okay? Data sets may be available in different forms, right? Either there's a readily available data sets online, right? Kaggle has quite a few of that. There are also other kind of data like sharing platforms that you can grab a lot of data, okay? But still there's a bit of difference, right? Some data are kind of say nicely cleaned, curated, so you basically just take the data and run things on top of it. Versus some data are coming from the real world. It's a little bit messy. It takes time for you to understand what they are. It takes time for you to kind of assemble the different types of information. There'll be various data quality issues, okay? But don't shy away from the real world data because that's the real world, right? If you want to work on a real project, right, look at the data, but you need to be aware of the potential issues with your data, okay? I also got a question about, can I just scrape the data? Scraping used to be done a lot more, because that's at the early stages when people just put that data there, they don't care who's using it, they're fine. But nowadays, actually, most of the places, okay, they are more protective of the data. If you check their terms of service, many of them say you cannot scrape at all. Many of them have like a monitoring mechanism, they will blacklist you very quickly, okay? And it's just probably against the terms anyway to be scraping, unless they explicitly said it's okay, all right? So I wouldn't count on scraping, okay? And try not to do it. So think about, yeah, what kind of data sets are already available? Another one is about APIs, okay? Many places, if like they may have various kinds of like APIs for you to access the data, okay? Some of them may have limit, right, in terms of how many requests you can get, how many like queries you can submit during any particular time period. So all those things you need to check. So that's why I say, as you're formulating your project, okay, really look into the data availability aspect, where you can get the data, how easy it is to get data, how good the data is, whether you have enough to do what you need, okay? That's the data sets. What problem do you want to address, right? So you have some data, and you may have some question you always wanted to answer, right? So start thinking about the focus of your project, okay? This is where the team brainstorming can be very helpful, right? You have like some area you're interested in, you have some data sets. Now you can just start asking questions. It's more like, yeah, your wish list, right? What things you would like to answer, okay? Come up with a long list. Longer the better, really. Because this is the brainstorming. Even if you don't get it all finished for this course project, it's still very good practice. Because in the real world, with any like data scientist position, right, you want to be creative, right? You want to be able to ask those questions that people haven't thought about and actually maybe bring out a value from the data. So come up with a list, okay? And then maybe try to prioritize or shuffle things around a little bit based on what's available, what the team is able to do, okay? And then, of course, you really need to ask yourself, right? Why do I want to work on this project, right? Why those problem or questions are particularly interesting or important to address, okay? This actually connects to the knowledge extraction, connects to the application scenarios, right? Like why it is important for you to figure this out. Okay, sometimes, oh, I don't know, I'm just thinking, I'm curious, I want to know, fine, right? But at least like do that reasoning. But many times you'll say, okay, if I can find this, I may be able to use this information for something, okay? Some bigger things, right? Traffic patterns. If you have a way of knowing the traffic pattern, right? We had the football games. If you have some way of knowing where will be particularly congested, where it's easy to find parking, or what kind of food service you may have on campus, all this information can be readily utilized, right? You probably can find value. Or if you're looking for, like, say, the housing market, air quality, something like stock price. That's like a very typical, right? But many of those, as you pull out, right, the information, the answers you're looking for, then think about how this can be useful. Okay? Challenges. Okay, this also relates to the fact that, okay, if it's straightforward, yes, you can do it, but I want you to bring out value, right, through your work. So that means I'm answering some questions that haven't been answered before, or I'm trying to come up with some solution that people found challenging, or this is like there's some solution, but it's just not good enough. I'm trying to improve it, right? So think about, right, what is your contribution, okay? And because the existing solution are not good enough, right, that's the potential, like, contribution of your work. What has been done before, limitations. Okay, so I encourage you to check what has already been done. You can utilize existing tools, you can existing data sets, techniques, or whatever other people have done already, so you can build upon it, right? We don't need to be reinventing the wheels, right? There's actually a lot of things available, right? So utilize those. And then say, okay, given what has been done, seeing the potential gaps or limitations, right? We are trying to do this, okay? All right, I want to highlight a few practical issues. Because the previous slide says how you choose your project, right? Some people say, oh, it's already hard enough to figure out, like, my teammates, the data sets, right, and all that, okay? But to actually get to the point of working on your project and have something finished, right, by the end of the semester and present, right, your results, there are a few things I want to really kind of emphasize. First one, data access, right? I cannot emphasize more. Make sure you get the data up front. You know you have the data. But also this gets to the data management, okay? I literally had students like losing their either the raw data or losing their intermediate, like code, whatever, towards the end of the semester, okay? Even though, well, nobody wanted that to happen, but that could happen, okay? So just make sure if you're working as a team, like agree upon, like, the mechanism of, so, okay, where the data will be hosted, how you can have maybe backup, how it's easy to share across the team members. So just say where you're going to manage your data, okay? Some teams that have leverage, for example, like maybe Excel spreadsheet is good enough, CSV files are good enough. Sometimes they may have some shared folders or something, right? So just have a way to easily manage your data, the intermediate results, your code, all that, okay? This actually relates to the code management as well, right? Think about whether, like, say, how you can easily maintain that, like some kind of versioning repository may be helpful. Things that will be easier for you to manage, right, your progress. Okay, evaluations I will also highlight. Okay, as I said, like when you think about your data mining project, before you even come up with a solution, right, within the black box, you have some way of saying, okay, how do I evaluate, right, the success of my project, right? So think about how you're going to do the evaluation. Sometimes say, okay, just better accuracy, more efficient processing, or just say I found some results that are actually really useful. Those kind of mechanisms, or the insights are useful. But how do you claim that, right? Particularly, right, when you have to get feedbacks or responses from others. Because I've had teams, like say they want to work on recommender systems. Every year, actually, we'll have a few projects on recommender systems. But then the question is that either you have some benchmark that you can compare against, right? To say that, okay, this is the kind of performance they get with my solution. But some teams say they start by thinking, oh, I want to ask my friends to give me feedback. Okay, fine. But how many friends do you have? How much time do they need so that you have a sufficient number of responses to claim this is better than whatever the baseline you're comparing with, right? Just think about the practicality about how are you going to show or convince people, right? So if that's what I say, whenever you say asking people to give you feedback, yes, for a small scale, but you probably need a more scalable solution if you're talking about like a general evaluation, okay? Computation platform tools, this also gets you, as you're thinking about the scale of your project, right? Some of you may say, okay, maybe between our shared machines, we're probably fine. Some of those I can leverage online resources, right? For example, most of the cloud computing places, they have free credits for students. Okay, if you haven't utilized that before, you can look into that. And for this course, of course, I don't require you to work with huge amounts of data or large scale, but I want you to at least explore the scaling factor. Meaning that, let's say, if my code works fine on my laptop with say 100,000 data points, and now like if I'm going to work with 1 million data points, right? Would that still work? How would that scale, right? So think about how you want to cope with the potential like computation need, okay? And of course, feel free to talk with us. We don't have a dedicated computing resource allocated to the course, but like we usually can point you to resources that you may be able to leverage, okay? Team coordination. I don't know how many of you have worked on like team projects before? Everybody, or, okay? Was it mostly successful, happy? Sometimes, right, depends, right? Hopefully, like you probably have seen like most of the good side, right? But it can be challenging, right? Because like say, like everybody's busy, especially when you get to the middle of the semester, end of the semester, like all kind of things come up, right? Coursework, all the different exams or other things, it'll be difficult. Everybody will be busy, right? So first thing, I would say as a key team, make sure you come up with a coordination mechanism ahead of time. Do you want to do maybe weekly check-ins, or you have some kind of communication channel so it's easy for all of you to kind of get like synchronized quickly? Really, like be a good team member, right? If you have to miss out something because you have another deadline, let your team member know, right? The worst will be that you just disappear, not responding to anything, and don't do your work, right? That's hard for everybody, okay? So just think ahead of time, but also just as a team, right? It's easier to discuss this upfront than later on when the issues arise and it's much more challenging to have that conversation, okay? But at any point, if you need me to talk to the team members, I'm happy to do it. But I say, just keep that in mind, and I say everybody, right? Just value the time of your team members and try to be a good team member. This is the last piece I want to highlight, okay? This is 40% of your final grade. You're working on group projects, but we are also looking at individual performance, okay? So on one side, right, don't feel that, okay, you can, if one of your team members is not doing as much, we try to, of course, like we try to get everybody to have a sufficient contribution, right? But if there is a kind of imbalance contribution in the team, right, we will be reflecting that in the individual grade, okay? So that's one. Second, for the other side, right, if you're not contributing to the team enough, then don't expect you get the same grade, right, as your teammates. So that's what I say. As a team, we want to work together. We want to have a good project together, right? But then you know that like each of you really make sure you have sufficient contribution. Okay, so some of the logistics. I think we'll have a few minutes, right? So by week 5, we're going to post this link for you to submit your project proposal, okay? So what goes into your project proposal? Come up with a project title, informative one, okay? Every year I would say, like, I don't want to see, let's say, data mining project as your title. Please, come up with something that's a little bit more informative, right? Pick some keywords so I can quickly remember. When I see your title, I know which team you're in, which project it is, right? Okay, so start with a good title. And then for your team, list the team members. And we do need to see, right, 4502 versus 5502, because we do grade. We have different bars, right, for the undergraduate section versus graduate section. So list that out, okay? And if you already have figured out something, like say the expertise, for example, like this student has some background in this, so he will be leading some effort. So if you have something, feel free to list that out, but you don't need to spell out all the details. But just knowing that as you're talking about the team, especially towards the very end, we'll be asking which team member worked on what's their individual contribution, okay? Problem statement, so just a brief, right, description of what kind of problem you're working on. That's more like your motivation, right? Why you want to work on this problem, what is this problem about, and then like a little bit is about like what has been done, so literature survey, right? I mean that you don't need to do an exhaustive one, okay? But I want you to at least do a reasonable effort, right? Searching online, searching related sources, you know, like generally, right, what has been done, okay? So you can talk intelligently about, okay, I know the field, okay? I know what has been done already, mostly, right? And then that is why I'm kind of claiming my potential contribution of this work. All right? And then proposal work, right? This is data set, it's still just a proposal, so don't worry about having everything spelled out, but at least I want you to have some description about what kind of data you're going to use, whether you have it already, if not, how you're going to get it, right? And also some of the high level, right? Mentioning of say, okay, we're going to do maybe correlation analysis, we're going to do some kind of classification or image processing or text sentiment analysis. If you have some of those ideas, put it in. You're not bound by that anyway, but that's just a way of showing this is the proposal stage, right? Whatever that you have in terms of what you're thinking of doing is good to be presented there. Evaluation, okay? So here, even if you cannot spell out all the details, but at least have a good reasoning, right? A plan, okay? Say, okay, given my problem setting, okay, this is how I think it'd be important to evaluate, right? So if you care about the efficiency, you care about the accuracy, false positive, false negative. Those terms we'll actually cover more later. But at least based on your problem setting, talk about how you would like to evaluate, okay? How you demonstrate success. Milestones, that's basically just a way for checking your timeline. By the time you do your proposal, that's week 5. We finish in week 16, okay? And then we have a checkpoint. That's week, I think I have it on the next slide. Yeah, so the timeline. Week 11 is our checkpoint. The final point is week 16. Okay, so just keep that in mind. And then based on your team schedule, right, you should already check when you have exams, when you have some kind of major projects due from the other courses so that you can coordinate a little bit. So that, okay, I think we can do more during this time period. We can do probably not much during this time period. That's all fine, right? Just plan out the remaining 10 weeks or so, okay? So these are some specific terms, and also in Canvas for your submission, we'll be providing some instruction about what goes into your proposal, okay? So besides your proposal itself, we actually will also ask every team to do an announcement. That's to everybody. So do an announcement. That's actually in Piazza. So I want you to announce what your project is about. Who's on your team, what you're going to do, maybe brief mention about what data you want to use, what kind of tools. So that's just a way general for the class. We learn from each other, okay? I'll show you. By then you will see there'll be a wide variety of projects, okay? That's why it's interesting, right? Okay, and then with the proposal, we also can do presentations, so you get to present your ideas to the, I don't know how many students, it's not required for everybody to show up, but you'll be presenting to myself, the TAs, our graders, so we'll be providing feedbacks. Okay, that's all for today, okay? We'll see you next week.